Now, in the previous lecture, we discussed the octal phase shift keying or 8-PSK, and now it is time to take a couple of examples. The first example is one where we will be, in fact, this is a kind of analysis type example, not a numerical example, so to say. So here we will be, in this example, we will be, the question is rather, the analysis is posed as a question. The question is that we have to determine the bit error rate or the probability of bit error in Qpsk. We have to determine this and relate it to bit energy. So before I proceed with the solution or the analysis, before I carry out the required derivation here, I would like to just recall your attention to the fact that in Qpsk, what we derived earlier was the symbol error rate or the probability of a symbol being detected with error, which is the same as the probability of a signal being detected with error, a signal being detected as something which is not that signal is. So, for example, S0T being detected as S1T or S2T or whatever it is. So, that is what we did earlier. So, earlier we determined the symbol error rate or the probability of error in detecting signals, but now we have to find out what is the bit error rate or the probability of error in detecting the bits. And recall that in Qpsk, a symbol is made up of 2 bits, that is a die bit. A symbol is composed of a die bit. So what we notice is that in lecture 12, I remember we had derived the, so if I just quickly draw the Qpsk constellation, the signal space in phase and quadrature, we call these type of errors, that is, say, a signal point or a symbol being detected as the one which is closest to it, the adjacent ones. We call those, in this discussion, we call them as adjacent errors. And this type of errors where signal is detected as one which is diametrically opposite to it, we'll call it as the diametrically opposite type of error, just for our convenience. So just this is the picture. So these type of, and you know, these type of errors will dominate. And we will proceed with the assumption that, which is a perfectly valid assumption, that's how it happens in reality. We will proceed with the assumption that the die bits are mapped onto the signal points, or the die bits which constitute the symbol are mapped onto the signals using a gray coding scheme, so that these type of errors will result in only a loss of 1 bit. So if you detect this as this, you lose only 1 bit, you get the first bit correctly, whereas these type of errors you will end up losing 2 bits invariably. You can't do much there, but fortunately these type of errors are less probable compared to these type of errors. So with this background, let us quickly try to determine the bit error rate or the probability of a bit error in Qpsk. So we saw in lecture 12 that probability of adjacent type errors. I just now explained what I mean by adjacent type errors. Probability of those adjacent type errors was determined to be 2q square root of es by n naught minus 2q square root of es by n naught to the power 2. So this was this was done in lecture 12. I had derived this by going through certain steps, certain detailed steps. So I'm just writing down the result here. So 2q root es by n naught minus 2q root es by n naught the whole square. That is the probability of adjacent type errors. That is these type of errors. And the other type of error, that is which I call as the diametrically opposite type of errors. These type of errors, the probability of such errors occurring is q root es by n naught the whole square, and the sum of these two will give you the probability of error in a symbol, because a symbol, if it is detected erroneously with error, is detected as some other signal, then the possibilities is that it's either detected as one of the two adjacent ones or the one which is diametrically opposite. So if you add these two probabilities, you will get the probability of symbol error in Qpsk. That's all known. We have done that earlier. Now let's say that let's say that with gray coding, of course, with this type of mapping of die bit, let's say that a total of n symbols were transmitted. Total of n symbols were transmitted, and each symbol is composed of one die bit, so that means a total of 2n bits were transmitted. Now out of this n, let's say m symbols are detected erroneously. That is, we have made error in detecting n. Out of n symbols, we have made error in detecting m symbols. Now, for sufficiently large value of n, huge values of n, m by n will be the symbol error rate. So, probably you might have sent something like 10 power 6 10 power 6 or even 10 power 20 symbols, just to give a feel for the numbers. And if you end up getting, so let n be 10 power 20, and out of 10 power 20, let's say we have detected 10 power 10 erroneously, in the sense we have made a mistake in detecting 10 power 10, then the symbol error rate is, so small m is this, capital M is this, the symbol error rate is out of 10 power 20, 10 power 10 have been detected erroneously. So that means the symbol error rate is 10 power 10 minus 20, that is 10 power minus 10. Just to give you some numbers here. So m by n is the symbol error rate. M by n is the symbol error rate, and the symbol error rate, as you know, is the sum of these two, because symbol error rate is the probability of error in detecting a symbol. So symbol error rate is the sum of these two, because this accounts for the adjacent type errors and this accounts for the diametrically opposite type errors. So that means m by n has to be this, which means that the number of symbols m by n has to be this. Remember, m by n is the symbol error rate and this is the symbol error rate, the sum of these two. So m by n has to be this, which means that the number of symbols which we have detected wrongly will be equal to the sum of these two multiplied by m, because multiplied by n, because m by n is this. M, the number of symbols where we have made an error in its detection, will be n into this, and hence the number of symbols which we have lost, that is lost in the sense we have made a wrong decision, will be 2 n q root es by n naught minus 2n q root es by n naught square plus n q root es by n naught square. So this is the number of symbols which we have lost, in the sense number of symbols in which we made an error in its detection. And you can see that if you divide this by n, you will get the symbol error rate, which you should. Okay. Now we note that this is the probability of adjacent type errors, or these are the number of symbols out of the symbols which we have lost. These are the number of symbols which we have lost due to an error of the type wherein we detect a signal to be one which is adjacent to it. And these are the number of symbols which we have lost due to the type of errors where we detect a symbol to be the one which is diametrically opposite to it. Because this is the probability of detecting a symbol as one which is a signal as one which is diametrically opposite to it, and take away this n and you get the probability of a signal being detected as one which is adjacent to it, which means that, and you know that whenever a signal is detected as one which is adjacent to it, or a symbol is detected as one which is adjacent to it, you lose one bit. That is because of the gray coding. So these many 1 bits we have lost, because this is the number of symbols which we have lost due to the type of error wherein we detect one as the adjacent symbol, and whenever that happens you lose 1 bit. So if you have detected a symbol as one which is lying adjacent to it, you have lost 1 bit. So these are the number of 1 bits that we have lost, and whenever this happens we end up losing 2 bits. So these are the number of 2 bits that we have, number of pairs of bits that we have lost, because this is the type of error wherein we detect a signal as one which is diametrically opposite to it and you lose 2 bits. So these are the number of pairs of bits which you have lost. This is the number of single bits which you have lost, and that means the total number of bits lost will be, you simply have to add the bits. So this many pairs of bits, that means 2 into this bits lost, and 1 into this many bits lost. Remember, whenever this is the probability of detecting a signal to be one which is diametrically opposite, you lose 2 bits, and these are the number of such losses in the symbols. That means this into 2 will give the number of bits which you lose due to such errors. 1 into this gives you the number of bits which you lose due to the adjacent error. So total bits which you have lost will be 1 into this plus 2 into this, and that gives us 1 into this is this itself, 2 into this will bring a 2 here. When you add, these two will get cancelled and you will get total bits lost as equal to 2n q root es by n naught. These are the total bits lost. Now if you divide the total bits lost by the total bits transmitted, you will get the bit error rate. So total bits lost divided by total bits transmitted. I told you that there n symbols are transmitted and each symbol is made up of 2 bits. So total bits which were transmitted is equal to 2n, n into 2. A symbol is made up of a die bit, 2 bits, and this means that the bit error rate in Qpsk is this. This is the bit error rate in, or bit error rate of Qpsk is this, q root es by n naught. So first part of it we have saw determine the bit error rate in Qpsk, and relate it to the bit energy. Now we note that a symbol is equal to 1 bit, sorry, 2 bits. Symbol is made up of 2 bits. So this is the symbol energy. So one symbol energy is equal to the energy of 2 bits. So 2 bit energies, when you add 2 bit energies, you will get one symbol energy, because one symbol is made up of 2 bits, which means that bit energy is ES by 2, or ES is 2 EB, and hence we can express the bit error rate in Qpsk in terms of bit energy like this. So this completes the second part. Q of root 2 EB by N naught. And if you have been following the lectures carefully, you will observe that this is the same. This is the same as the bit error rate in binary PSK. This is the same as the bit error rate in binary PSK. Now that shouldn't come as a surprise, because if you go back to the schematics of Qpsk, you will recall that basically in Qpsk what happens is, this is what basically happens in Qpsk. We transmit two binary PSK signals. If you take a look at that transmitter schematics, Qpsk generation schematics, you will see that this is what happens in one of the arms. This is what happens. This represents one of the bits of the die bit. It is multiplied by a carrier, and this being plus or minus, what you get here is essentially binary PSK. And then you have the lower arm like this of the transmitter schematics or generation schematics. So if you see this, these are two binary PSK signals. This is also binary PSK. The only difference is that with reference to this, there is a phase shift of minus pi by 2. That's the only difference. And that difference is important in the sense, because of that difference, these two signals are orthogonal. They are orthogonal, and hence we are able to separate them out. And what we do is we add it up. Of course, there is a multiplication with a negative sign, which is not significant here. So you just add it up and transmit it. And at the receiver, what you do is you detect R1 and R2 independently. You detect R1 and R2. You are able to detect them independently because of the orthogonality. Please recall the receiver schematics. Because of the orthogonality, it is possible. These two are orthogonal, isn't it? If you multiply them and integrate from 0 to TS, you get the result as 0. So they are orthogonal. So two binary PSK signals are transmitted over orthogonal carriers, and they are in fact independent to each other. They are independent to each other because one can ask, why should they be independent? Isn't the noise which is getting added, because when you send the QPSK signal is a combination of this, but the noise which gets added to it is the same noise is getting added to this. But remember that at the receiver, N1 if is obtained, just go back to the receiver schematics and the functioning of the receiver. N1 is obtained as equal to 0 to Ts Nt, that is the noise which gets added, the sample function of noise which gets added into cos 2 pi fct dt, and N2 is obtained by 0 to Ts. Of course I have to normalize this, root of 2 by Ts root of 2 by ts nt sine 2 pi fct dt. Now it can be shown if you take the correlation of n1 and n2, if you calculate the correlation n1 and n2, expected value of n1 into n2 conjugate, n2 is real here, so conjugation is not necessary. Expected value of n1 and n2, if you do, it's a simple exercise, you can show that the correlation is 0. So n1 and n2 are not correlated to each other, and since nt is Gaussian, n1 and n2 are Gaussian, and uncorrelated Gaussian random variables will be independent. So the noise which corrupts this binary PSK and the noise which corrupts this binary PSK, when you split the QPSK as 2, are independent. So it is not necessary that the errors here will have a bearing on the errors that's going to happen here. The errors will be independent of each other. So the point here is that QPSK can be visualized as two independent BPSK signals transmitted over two carriers, that is carried by two carriers which are orthogonal to each other. In fact, they are orthonormal to each other, and hence that is why you see the symbol error, the bit error rate as the same as that of binary PSK, because it's nothing but two BPSK signals transmitted over practically independent carriers. Okay, now interestingly, from this idea, from this concept, it is possible to work backwards and arrive at an exact expression for the symbol error rate in QPSK. Now that's the one which that's what we'll do now. It's very simple now. So we can work backwards and arrive at the symbol error rate for QPSK. So what I mean by working backwards is that we receive, let's say there is one BPSK, there is the second BPSK, and they together form so this is over, say, cos 2 pi fct carrier sine 2 pi fct carrier, right? So you will get the R1 here, R2 here, and now a symbol is comprised of these two. A QPSK symbol is comprised of these two. Error in a symbol happens. There are three possibilities, the three ways in which an error can happen. R1 is received wrongly and this is received correctly. That is still a symbol error rate, because symbol is received with an error. Though you have received R2 correctly, the symbol, when you look at the symbol, there is an error. Next one is R1 received correctly and this is received wrongly. In the sense, there is an error in R2. Now again, this is a symbol error. Though you have received R1 correctly, when you look at it as a symbol, there is an error. And the third possibility is both are received with error. There is error in both, and then of course obviously you lost the symbol. So these are the three ways in which you can have an error in the symbol. You can have an error in the symbol. Yeah. So now the probability of this is that you should receive one with error, the other correctly, and the probability of error in binary PSK is the probability of error in binary BPSK is 2EB by N0, and as we saw earlier, 2EB is ES. This is the probability of error. So this is the probability of error on any one of these two, independent. So this probability, that is R1 being received correctly and R2 with error, is this into 1 minus Q root ES by N0. So you made an error here, that is the probability this. Along with that, you have detected this correctly. That will be 1 minus probability of error here. So because if there is a bit, you either detect it correctly or you detect it wrongly. So this is the probability of this event. And due to the similarity, the probability of this event will also be the same. So this or this or this or this, together the probability will be 2 times this. So either this or this. results in this type of error. And this error, the third error will be Q, you have to have error in both the arms. So in two QPSK signals, VPSK signals, you should have error in both. So Q root ES by N naught whole square. And an error happens when this or this happens. This or this we have accounted for here by multiplying this with 2, or this we have to add this. Now the symbol error rate in QPSK is simply the result what we have here, and you can expand this and show that it is 2Q root ES by N naught minus 2Q root ES by N naught whole square plus Q root ES by N naught whole square. Isn't it? So 2 into Q is here, 2 into Q is here. That is a negative sign, and this is just over there, and you can simply see that the last two terms, one of them will vanish, and consequently the 2 becomes 1. So the result is the symbol error rate in QPSK is minus 2, and plus will become like this. And we have worked backwards. If ES by N naught is huge, you can neglect this. If ES by N naught is huge, you can neglect this, and the approximate symbol error rate for QPSK will be this, which we derived earlier. So with that, we will now move on to the next example. So this next example, this is a derivation type of example. So the derivation is posed as an example here, is posed as a problem here. So the question is, it's posed as a question rather. The question is to derive an expression for symbol error rate of M-ary PSK. So this is a generalization. So what is being asked is to get the symbol error rate of a generalized M-ary PSK system. Qpsk, in fact BPSK, binary PSK, quadrature PSK, and the octal PSK or the 8PSK become special cases of this. So if m is equal to 2, you have binary PSK. If m is equal to 4, you have the quadrature PSK, and then m is equal to 8 gives us the octal PSK. M can be 16, and so on and so forth. So the question is to find out the symbol error rate in general, the symbol error rate of a general M-aryPSK system. And in this, when we discuss this example, we will also see an alternate way to arrive at the symbol error rate. In fact, this by following using this method, it's possible to arrive at the exact expression. If you recall, when we derived the symbol error rate for octal PSK, that is 8PSK, we had approximated we had used the polar coordinate systems, and we had approximated the density function of 5. So here there is no such approximation, we will get an exact expression. Okay, so this is the way we will proceed. As we did Earlier, we'll first find out the probability of correct reception of a symbol, and then we'll subtract that from 1 to get the probability of error or the symbol error rate. So the signal space diagram and the constellation will be like this. So this is the in phase and the quadrature axis, and we will have, let's concentrate on the signal S0, and since it's an M-aryPSK, S1, S2, so on and so forth we'll have, and to complete the circle or to come till the last symbol, I'll just write signal, I write Sm-1t, and as we know already, this will be two pi by m, and this will also be 2 pi by m. And you can see that if m was 8, that is octal PSK, if m was 8, this would have been pi by 4 and this would have been pi by 4, that means minus pi by 4 and pi by 4, as you know. And if m were 4 Qpsk, in that example we had seen the Qpsk constellation, we had the 4 symbols like the signal points over here. So if m is equal to 4, you would get pi by 2, pi by 2. Okay, so in general it is the angle between the two adjacent signals will be 2 pi by m in general. Now the decision bifurcation will be like this. So this region will belong to the signal S0t. So it will be pi by m here minus pi by m this side, that means pi by m this side, pi by m this side. Again in octal PSK, if you recall, it was pi by 8 minus pi by 8. So this we'll just draw a bigger version of this. We'll concentrate only on this. We'll find out what is the probability of S0t being detected correctly, and then we will deduct that from 1 to get the probability of error in symbol S0t. And again, due to the symmetry and the fact that the noise is additive right Gaussian, we will the probability of error in any of the symbols will be the same. So I will draw a slightly bigger version of this so that it becomes clearer. That got a bit cramped towards the end. We will have in phase and quadrature, and I just draw a slightly exaggerated version because I need space to show certain, I need space so that I can mark certain things here. This is S0, and the bifurcation, the decision region will be, this angle will be pi by m here and pi by m here. So minus pi by m, pi by m, and the signal S0t is detected correctly whenever the point described by R1, R2 lies in this region. Given that, of course, S0t was transmitted, you have R1 and R2, and if R1 and R2 describes a point which lies here, you have detected the signal S0t correctly. And here onwards, I will just introduce a new notation, in the sense a slight difference here. Here onwards, maybe we can call, because this is the phi 1 and phi 2, and this becomes in phase carrier component and quadrature carrier component. And instead of calling R1, R2, we will here onwards call Ri, Rq. So Depending on the situation, context, you should understand. Ri is refers to the R1 which we discussed earlier, and RQ refers to the coordinate here, that is R2 which we had earlier. Now we can write expression for these straight lines. We can write expressions for these straight lines, and the slope is tan pi by m. From elementary algebra or geometry, you know the slope of this is tan pi by m. So the equation of this line will be RQ equal to, that means on this line RQ will be equal to tan inverse pi by m, which is the slope, into Ri, and the y-intercept is 0. So this is the equation of the line that you have here, and the equation of this line will be slope is negative, everything else is same, so RQ is equal to minus tan inverse pi by m Ri, and signal S0 t, or the symbol corresponding to the signal S0 t, is detected correctly whenever RQ is less than Ri tan inverse pi by m, or more than minus Ri tan inverse pi by m. So RQ equal to tan inverse pi by m Ri is this line. So whenever RQ is less than this value, whenever RQ takes a value which is less than this, RQ will be in this range, and simultaneously it has to take a value which is greater than this. So we can say that whenever RQ is in this range of values, the point described by R1 RQ will be in this region, and hence the signal S0 is detected correctly. So whenever S0 is transmitted and Ri RQ is such that RQ satisfies this relation, then you have detected the signal S0 correctly. So now we can also write this as, you can subtract RQ from both the ends, you will get Ri tan inverse pi by m minus RQ and minus Ri tan inverse pi by m minus RQ. So Ri and RQ, if signal S0 is transmitted and Ri and RQ are such that this is greater than 0 and simultaneously this becomes less than 0, you will end up detecting that signal S0 correctly. Now we quickly recall a very elementary fact, which is, suppose you have x as a random variable and it has mean mu x and variance sigma square x. Let's say its mean is mu x and variance is sigma square x. Now let's define a new random variable y, which is equal to alpha into x plus beta, where alpha and beta are deterministic values. Alpha and beta are constants, they are deterministic value. Let's make it alpha x minus beta, so that I can make it easier when I relate this with what I have here, because I am subtracting something here. Okay, right. Now expected value of y is the mean of y, and that will be expected value of alpha x minus beta, which will be alpha into expected value of x minus beta, because expected value of beta is beta, and alpha being deterministic, it has its value alpha, and expected value of x will be mu x. So expected value of y is this, when x has an expected value mu x, and you define y as equal to alpha x minus beta. So if you multiply x with a deterministic constant, its mean gets multiplied by that, and if you subtract simultaneously from that beta, this is getting subtracted by beta. So that is the first thing that to be kept in mind. These are elementary things, you probably know this, but just for a quick revision. Similarly, if I try to calculate the variance of y, that means expected value of y minus its mean. If I try to find this, I get expected value of y is this, alpha x minus beta minus alpha mu x plus beta whole square. That will be expected value of alpha x minus mu x the whole square. That gives alpha square sigma x square. So what we see from this is that if you multiply a random variable x with a deterministic constant alpha and subtract beta from that, its mean becomes alpha mu x minus beta, where mu x is the mean of x, and its variance becomes alpha square sigma x square. So variance of x gets multiplied by alpha square, and the mean gets multiplied by alpha, and then beta is getting subtracted from that. Now let us concentrate on this relation that we have here. Let's concentrate on this relation that we have here. We could see that Ri and Rq are random variables, and Ri is getting multiplied by tan inverse pi by m. Similarly, Ri and Rq random variables, Ri is getting multiplied by minus tan inverse pi by m, and Rq is getting multiplied by minus 1. So point is, Ri and Rq are Gaussian random variables, and mean of Ri, remember Ri is the in phase coordinate of the signal point, not the signal point, in phase coordinate of the, or rather Ri is the projection of Rt onto the in phase carrier component axis, and the mean of that, when S naught t is the transmitted signal from the signal space and the constellation which I had drawn earlier, you could see that the mean is root Es, because S naught t's coordinates were root Es 0, and the mean of Rq is 0, because again S naught t's coordinates were root Es and 0, and variance n naught by 2, variance n naught by 2, and they are Gaussian. Now what happens when you multiply Ri with tan inverse pi by m? What happens to its mean and variance? From what was discussed just now, its mean will simply get multiplied by tan inverse pi by m. So mean of this as a whole will be root Es tan inverse pi by m, and variance will be, the variance of Ri is n0 by 2. If you multiply with tan inverse pi by m, the variance becomes n0 by 2 tan inverse pi by m whole square. And of course RQ mean is 0. If you multiply with minus 1, mean remains as 0 itself and variance remains as n0 by 2 itself. And of course similarly we can say that mean here becomes, mean of this as a whole will become 0. Sorry, mean of this as a whole will become minus root es tan inverse pi by m, and variance will be the same as n0 by 2 tan inverse pi by m whole square. Right. So we basically see that, and multiplying Ri tan inverse pi by m will not change its statistical properties, in the sense, of course, its mean will change, variance will change, but the statistical nature, the Gaussian distribution will not be affected. So basically what happens is we have added two Gaussian distributed random variables here. This is one of them with mean as given here, variance as given here. This is the other one, including the negative sign. Minus RQ is added with Ri tan inverse pi by m. When you add two Gaussian distributed random variables, the result will also be a Gaussian distributed random variable, and its mean will be the sum of the mean of these two, and its variance will be the sum of the variance of these two, which means that what we have here, if we identify what we have here as the random variable, say I will use x. If what we have here is x, then we have the density function as 1 by root of 2 pi into sigma. Sigma is square root of the variance, and variance is the sum of the variance of this and the variance of this. Variance of this is n0 by 2, variance of this is n0 by 2 tan inverse pi by m whole square. So that will be 1 plus tan inverse pi by m whole square into n0 by 2 under root. And this 2 and this 2 will cancel. Right, and e power minus of x minus, what is the mean? The mean is the sum of the mean of the two. The mean of this is 0, the mean of this is root es tan inverse pi by m. So mean will be root es tan inverse pi by m. X minus root es tan inverse pi by m whole square divided by 2 sigma square. Sigma square is this what you have. So in fact sigma square is this what you have here with a 2 here. So 2 sigma square will give us 1 plus tan inverse pi by m square into n0. Remember this is e power, so probably I should write e power. It's e power. Hope that's clear. Got a bit of shortage of space here. And if I call this as y now, as random variable y, not the y is equal to alpha x minus beta, that example is over. That was just to demonstrate something. Now this is, if I call this as y, be equal to one by, so I will not explain the steps, I will simply write down the result. Here I have explained in detail, so same thing, same argument. E power, that should have, it's e power actually, so e power minus of x plus root es tan inverse pi by m whole square by 1 plus tan inverse pi by m whole square into n naught. Now, since we have these expressions with us, we can easily find out what is the probability that y is this, the random variable which is described by this density function, takes a value less than 0, and what is the probability that x, that is this, takes a value greater than 0 simultaneously. When that happens, the signal S1t, S0t is detected correctly. So that will be the left hand side, that is the probability of this taking a value greater than 0 will be to infinity dx, because the density function of what we have on the left here is this, and probability of that taking a value greater than 0 will be 0 to infinity of this integration. And this will be, that is probability of what we call as y here taking a value, that this is our y, it taking a value less than 0 will be this integration. Now, I am sure you have enough knowledge, if you have followed my lectures, to evaluate this on your own. So I'll just quickly go through the steps. Let us define x minus root es, not a definition level, we are going to make a substitution. X minus root es tan pi by m divided by square root of n naught by 2 1 plus tan square pi by m, or rather 1 minus tan square pi by m. There is there is an error which I have made, which you might have. There is an error here in the sense I should have taken the slope of the lines as, that is the line which is there on the top, as rq is equal to ri. Slope, not the slope, the equation. In fact, slope should be tan pi by m. I took it as tan inverse pi by m. I have put a footnote at that point now, but please, I just want to reiterate that I made a mistake there. I put a footnote there, so that is addressed now. So instead of tan inverse pi by m, I should have used tan pi by m. So now I am making that correction. So till here, wherever it is there, it should have been tan pi by m. I am really sorry for that, but hope that will not be a serious problem with you in understanding, because I have put there in the footnote itself, and if you have been careful enough, you might have caught me earlier itself, right? Okay, so this is the, if you make this substitution, so I will just change it here itself, because I still have it here. I will make the correction. It's not tan inverse pi by m, it is tan pi by m. Okay, done. It's better that I caught that mistake now itself. Okay, so make a substitution. Make this substitution here. Say, call this as u. And then if you make the substitution and evaluate this, similarly, you make a substitution, say y plus, this must have been y, an error because I had y here. So y plus root es tan pi by m divided by n0 by 2 n0 by 2 1 plus tan inverse, sorry, again I am going to tan inverse, I seem to make a lot of mistakes today. 1 plus tan pi by m under root tan square. So if we call this as, say, v, make these substitutions here, and of course, as you know, the product of these two integrals will give you the probability that x is greater than 0 and simultaneously y is less than 0, and that is when, and remember, x and y are derived random variables from Ri Rq relation. So the product of these two gives you the probability that the signal S0 t is detected correctly. So make these substitutions here and evaluate them. You will be able to write them in terms of the Q functions. That I leave it for you. You will be able to write it in terms of Q function, and the final result will be probability of correct detection will be 1 minus, this is the probability of correct detection of the signal S0 t root 2es tan pi by m divided by square root of n0 1 plus tan square pi by m, this whole square. This is the probability of correct detection of the signal S0 t, and hence this is the probability of correct detection of any of the symbols, and hence the probability of wrong detection will be 1 minus this, and 1 minus this will give you 2q square root of 2es by n0 sin pi by m. So I put sin pi by m because this is sin by cos, this is sin by cos square, so sin square by cos square plus sin square 1 by cos square, and it's under the root, so 1 by cos, sin by cos, that will give you sin, and minus q square root of 2es by n0 sin pi by m the whole square. So get them, fill the missing steps. I have skipped a few steps, especially the q function derivation. I have taken you up to that substitution which I knew the q function. So fill those steps and arrive at this result. Now quickly you can put m as equal to 8, and you see that when you put m as equal to 8, the exact error probability of 8 PSK you get. This is usually, we neglect this because this is for large values of ES by large values of this argument, this will be negligible. So we usually neglect this, and for 8 PSK you will get the probability of symbol error as roughly equal to this with m is equal to 8. For Qpsk you substitute m as equal to 4. Sin pi by 4 is 1 by root 2. Root 2 cancels, you get 2q es by n0 minus q root es by n0 whole square. This is exactly the expression which we got earlier. So this is the generalized expression for the probability of error of M-ary Qpsk, M-aryPSK, not M-ary Qpsk. And you can see, for as m becomes larger and larger, this term becomes more and more considerable compared to what it would have been for smaller values of m. So what is happening is that as m becomes larger and larger, the points on the constellation become closer and closer, because the angle between them is 2 pi by m. It has become closer and closer, and hence the types of errors which are not just the adjacent errors become significant. That is why this term becomes more and more significant as m becomes larger and larger. So with that we will end this lecture, and we will continue further in the next lecture.